Motion is what it's about. All humans spend every waking second thinking about motion. You're either trying to predict the motion of something or you're trying to control the motion of something. Look at what Amazon does. Look at the motion that they're trying to control. Look at what Boeing does with its airplanes. Look at what surgeons do and nurses do in the hospital. I mean, every aspect of human life involves motion, and our goal is to be successful in predicting or controlling motion. So, but it also turns out that motion is changing position. So we can't talk about motion unless we have a really, really good, solid way of saying where things are. And saying where things are in the universe is position. What are we going to use? Well, right now there's a problem, because imagine that this plain white sheet paper went in all directions. There'd be nothing to refer to. I wasn't here. Where's Tony? Who knows? But we introduced this thing called a frame of reference, and voila, suddenly we can just say all day long with great precision. If we want precision, we can say where Tony is. All right, so what is a frame of reference? It's basically a set of coordinate axes, and how many you need. You know, we have 3 in our 3D spatial life, X, Y, and Z, and how many you need depends on what your object is going to do. So this green straw is supposed to represent an axis. Could be the x-axis. It's just a straw, right? So you got to imagine it going off in all directions. But I got these little tick marks. They're a centimeter apart for our purposes. And suppose that Tony promises that he's only ever going to move this way, and he's only ever going to move this way and that way. Could we get away with just using one coordinate axis? Could we just get away with using an x-axis? And the answer is yes. Okay, we'd have to extend it over this way, and we'd have to extend it that way. Or we would use measuring tape. We'd use something to record. But if all he ever did was go back and forth, then we would be good. Okay, but suppose that suddenly we find out that Tony is not just going back and forth, but he's also kind of wandering. He's never leaving the page, but he's always kind of wandering. Well, then suddenly one axis is no longer good enough. He will have an x position, but he can have an x, he would have the same x position being here and here, and so we would lose, we would no longer know where he was, because he could be anywhere up or down. Okay, so what are we going to do? What we're going to do is we're going to add another axis. This would be perhaps the y-axis. And so now, no matter where he is, as long as he stays on the page, you know, even over here, you got to remember this axis is going this way, this one's going down that way. So wherever he is, we could fix his position. He's going to have a certain 1, 2, 3, 4, 5, 6, 7, 8, he'll have a certain x position, and he'll have now a y position. So he'll have 2 positions really, one relative to the x-axis and one relative to the y-axis. What happens if Tony starts to, we're not looking, and suddenly he flies and he can go all around in 3 dimensions? What do? Well, suddenly this axis, you know, we can fix his position here, but now where is he above that? So guess what we're going to do? You already know. Yes, that's correct. We're going to add a z-axis, and now we've got him. Tony cannot do anything, and no matter where he is in space. Remember, again, these straws don't keep going, but the axes that they represent do. So no matter where he is in the universe, I can fix his position. All right, so we'll get rid of that. Tony, I still like you. You can hang around. All right, so basically we need a set of coordinate axes. How many? It depends. For 3D, you're going to need all 3 axes. That's something like a B or something to go in all dimensions. 2-dimensional means it's on a plane. Now, sometimes our plane is going to be a vertical. When we get to projectile motion, our projectile will always be, it will never waver left and right this way, but it'll go up and it'll go down. So we'll also still use 2 coordinate axes for that. We're going to start out with the simplest case, which is just a 1 dimension, which is a single x-axis. And that is, if we're going horizontal, we tend to use x. And if we're going vertical, we tend to use y. But as I put in my notes, that is simply what's called a convention. That means That's just how it's done. Okay, that's the way people have always done. I know you can't read that, but that's just because that's how it's done. So, and that's what a convention is. Nature could care less how many axes we use or what we call them. We're going to call them X, Y, and Z when we need them. And we use them X for horizontal and Y for vertical. Now you can see that Tony has been placed next to an X-axis because he's promised again to only do one-dimensional motion, not one-direction motion. This is two directions, but all in a straight line. Okay, so each dimension of motion has two directions. And he's just promised me that he's only going to move in one dimension, so we're back to an X-axis. Notice that if you're drawing a representation of this axis, remember the frame of reference does not require you to make lines on the ground. Let's see what's straight there. Okay. You can just, this can be in your head, but you need to have, to get this axis, you need to identify a positive direction. And by convention, meaning that's just how it's done, we put an arrow on the positive side. We also want to label our, if you are making a sketch of a frame of reference, then you want to label your arrowhead with X because that tells everybody that, oh, you're using the X-axis. And you need to have an origin identified. It may not need to be on your paper, but essentially you need an origin and you need to have some sensible units for the scale. And notice that in a frame of reference, an axis will always have a positive side and a negative side. And so here we are. We're ready to take Tony's position. And I'm only going to write this down one time. Tony, that's a little shadowy there. Tony's position is, right now, I'm not worried about sig figs, is 10 centimeters from the origin on the positive side. And you, if you were in class, you heard me say, I'm never going to write this again, and I never will. Okay, that's way too much to write. So we're going to come up with symbols to mean exactly the same thing. Now, notice that this is the X-axis. So we're talking about position. Oh, I forgot to even write. Tony's position is 10 centimeters from the origin of, oh my goodness, of the X-axis. I left that out. Yeah, of the X-axis on the positive side. So, since this is the X-axis, we're going to basically say Tony's position is 10 meters. Now, isn't that beautiful? How efficient that is? That's elegant. Its efficiency is so awesome, it's elegant. Okay, these mean exactly the same thing. I cannot emphasize that enough. This means exactly the same as that. Okay, this is shorthand, symbols. We're going to use a lot of them, but they're always going to have some wordy meaning behind them. Okay, so now let's think about, I can't show it on paper, but what if I put Tony eventually over here, he would reach a position of negative 10. So what do these two positions have in common and what do they have apart? I mean, what's different about them? Well, they're both 10, so they have the same magnitude. That's a word that we're going to be using all year long. Same magnitude, the same. Basically, we're saying is that the distance from the origin, maybe I should have made this negative 5 and 5, too late. They have the same magnitude. They're the same distance from the origin, but they're on opposite sides. So this is how we distinguish between which side of the origin you're on. Negative means on the negative side, positive means on the positive side. Okay, Tony's eventually going to start moving, and we want to be able to quantify that motion. We want to be able to describe it precisely, succinctly, efficiently, and motion is change in position so over time. And so what we need to do is we need to have a way of describing where Tony's motion. And the first thing we want to do is, Tony, you're in the way, is change in position. Well, not the first thing, kind of the thing that next thing we're going to do is change in position. Okay, I could write that all out in words, but basically change in position is, we need to get his, well, actually I'm going to write it out. Final position on the X-axis minus the initial position. I'm writing it out in words because I'm impatient and final position, because I know there is a much more efficient way to write this than change in position, blah, blah. Okay. All right. So by convention, meaning people before us decided this is how it's done. You can always invent your own system if you get enough people to follow along, but we're going to use the Greek symbol delta to mean change in. So change in is delta. Change in what? Position. We're going to use, since we're using an x-axis, we're going to use the variable x. Notice that we're not using p for position, because remember, we can have an x position, a y position, and even a z position. So p isn't going to work because there's which axis are you talking about? So change in x. All right. Now we're going to use the symbol x for position. So this is x minus x, but we know that's something's missing. So I'm going to go ahead and start using a new way, which is consistent with the AP. This is the AP equation sheet, which you'll be getting not too far from now. And it is x minus x sub naught, or x sub 0. Your textbook and I, up till this moment in time, do it slightly different symbols, but the exact same meaning. Is since we're using final and initial, we would use x subscript f for final minus x subscript I for initial, and we even start saying x sub f and x sub I. Okay, these are synonymous, so x sub 0 or x sub naught is your initial position, and x without anything is considered like that time in the future position. And final. Final doesn't mean this is where elephants go off to die and never move again. This just means, you know, you started your stopwatch, you looked at Tony. Well, for example, here you go. On your mark, get set, go. Tony at 0 seconds, Tony's at 15, and stop. And then 3 seconds later, he's at -5. 15 is your initial position, and final is either x sub f. You please use this if you're more comfortable. I'm going to start using this because this is what's on the equation sheet, and I feel like I should just use what's this year. I finally feel like I should do it for this year, so we'll see how it goes. All right, and then this is the future position or final position without anything there. Last thing I want to talk about is, you know, whose frame of reference wins? Or where should you put the origin? Does it matter? Which way should we make positive? Does it matter? And the answer to all that stuff is I don't care. Nobody cares. As long as you have your frame of reference in the same dimension as the motion, I could care less where you make the origin. Of course, you have to accurately track the position. You can't make stuff up. But I could care less. I don't care. I'm going to say whatever works best for you. A lot of times, 0 position works best for a starting position, but sometimes we're going to have scenarios where not everything starts at the same place, so you can't put everything at 0. So whatever just feels more convenient. Some people hate negative numbers, and so I'll do anything it takes to stay out of negative numbers. Okay, that's fine. Whatever works for you. All right, so we're going to show that we're going to have a battle between Big Al's frame of reference and JoJo's frame of reference. All right, they both are adequate for tracking the motion of Tony, because Tony's promised us that he's only going to go back and forth like this. And let's get started right there. Okay, so we're going to say on your mark, you set go. So when t equals 0 seconds, Tony is here. So this is going to be our x sub naught, or you could say x sub I if you want. And then that's 0 seconds, and then on your mark, it says stop. Okay, stop right there. Okay, and then this is going to be our x with nothing, or you could write x sub final if you want. Okay, we're going to see which one is the better frame of reference. Or does it matter? Okay, so what we're going to do is we're going to use both frames of reference to determine Tony's displacement during this 3-second interval. So here is Big Al's, and here is JoJo's. And Big Al is going to be, so the same equation, delta x equals x minus x sub naught. Same thing here. Hey, let me even just do x final minus x initial, not to confuse you, but All right, so let's see what we come up with. So we need, for Big Al, we need final position relative to his frame of reference, and that's going to be 15 meters. Let's go to JoJo's and see what her final position is, and it's going to be -5. They completely disagree. Different magnitudes, different signs, not looking good. Minus initial position for Big Al. Uh-oh, I messed up. I'll be back. Just kidding, I thought I'd misread the final, but now the initial. So let me see, the initial on Big Al is -5 meters, -5 meters, okay? That's Big Al. For JoJo, initial, 15 meters. Okay, again, complete disagreement. This is positive 15. The negative sign is there because that's the formula. It's getting a little bright. Oh, come in. All right, there you go, that's good. All right, so 15 and -5, completely different. Let's show you why I could care less which frame of reference you use, which way you make positive, which way you make negative. Because what is 15 minus -5? That is 20 meters. That's going to be a positive displacement. JoJo says, well, my displacement, or Tony's displacement, according to my frame of reference, is going to be -20 meters. And you say, well, okay, one good thing, they have the same magnitude, so they both agree that Tony went a certain distance, but they fundamentally disagree on the signs, and that looks, oh my gosh, but that's not a problem, because look, Big Al's positive direction is going this way, and Big Al said that Tony went 20 meters in this direction. Well, what does JoJo say? -20 meters. But look, JoJo's positive direction is positive there, positive direction is that way, so this is her negative direction. So JoJo said Tony went in the negative. But look at that. Get rid of that negative sign because they both agree. And that's why I don't really care what you use as an origin, what you use as positive, where you start your objects that you're tracking, because we're all going to come up with the same thing. Our initial and final positions may vary, but we're going to agree fundamentally on the one thing that matters, which is which way did Tony move? And both these frames of reference agree. So, and this is the idea that there is no absolute position. There is no master frame of reference. All position is always going to be relative to a particular frame of reference. There is no, like at the center of Milky Way, there is no like, this is the official frame of reference for our galaxy. It doesn't exist. Okay, that's it.